Swayam Prabha. Digital India. Educated India.
Very good morning. I welcome you all to the session of Thermal Engineering Basic and Applied, and in this lecture we shall solve two numerical problems on the gas turbine cycle, and I should say that these two problems are the last problems of this course. So, this is the first problem. Let me read out the problem statement first. A gas turbine unit or cycle operates on Brayton cycle, or a gas turbine operates on Brayton cycle between two temperature limits of 300 Kelvin and 1150 Kelvin. Find the maximum work done per kg of air and corresponding cycle efficiency. Then we need to show how does this efficiency compare with the Carnot efficiency operating between two same temperature limits. So, let us solve this problem. So, it is given T max equal to 1150 Kelvin, T min equal to 300 Kelvin, and we need to calculate what would be W net max, maximum work done per kg of air. So, air is the working fluid, right. If we try to recall, in one of the previous classes we could establish the maximum work done, that is the work done corresponding to optimum pressure ratio, because we never can achieve maximum pressure ratio, and that is equal to Cp into root T max minus root T min whole square. And if we plug in the value of Cp, that is for the air 1.005 kilojoule per kg Kelvin into root 1150 minus root 300 whole square, and if we calculate it, we will be getting these units would be kilojoule per kg, and this is equal to 276.62 kilojoule per kg, right. So, this is the maximum work corresponding to optimum pressure ratio, because maximum pressure ratio is not easily achievable. So, next we had to calculate maximum work done per kg of the working fluid, and so unit is kilojoule per kg. Next is we have to calculate cycle efficiency. So, we know eta cycle equal to 1 minus 1 upon Rp power gamma minus 1 upon gamma, right. So, this also can be written in terms of the maximum and minimum temperature of the cycle. This also we could establish that cycle efficiency corresponding to optimum value of Rp, it is 1 minus root T min divided by root T max, and if we plug in the value, it is 1 minus root 300 divided by root 1150, and this is coming as 48.92%. So, you can understand that cycle efficiency is less than even 50%. That is what we have discussed, or we have mentioned several times. So, this is cycle efficiency. Of course, this cycle efficiency is Brayton cycle efficiency. So, this is Brayton cycle efficiency. Now, we also could establish what would be the Carnot efficiency. That means, if we now consider that the Breton cycle is operating between two temperature limits, and considering the same temperature limits, if we consider the Carnot cycle, then eta Carnot cycle efficiency will be equal to 1 minus T min by T max, and that equal to 1 minus 300 divided by 1150, and that is equal to 73.91%. So, you can understand that Carnot cycle is one of the ideal cycles, and efficiency following the Carnot cycle should be certainly higher than the Breton cycle efficiency, and that is what we can see from this. Now, question is, the last part of this question was, how does this efficiency compare with the Carnot efficiency operating between two same temperature limits? That means, what we need to do, we need to consider eta Breton divided by eta Carnot, and that equal to, if we know this is the Breton cycle efficiency and it is the Carnot cycle efficiency. So, it should be certainly less than 1, and it is 0.66, right. So, Breton cycle efficiency is 0.66 times of the Carnot cycle efficiency. So, we can understand that gas turbine units, those run on the Breton cycle, efficiency is significantly small than the Carnot cycle. If we now move to the second problem, the problem statement is, a gas turbine operates on Breton cycle. For this unit, air is taken at 1 atmospheric pressure and 300 Kelvin. The air is compressed to 8 atmospheric pressure, and maximum cycle temperature obtained is 1050 Kelvin by using large air fuel ratio. So, it is already given that the air fuel ratio is very large, which in a way indicates that we can assume that the mass flow rate of the working fluid is m dot A only. Equivalent, that is mass flow rate of air only. The equivalent heat addition given to the combustion is 120 megawatt. So, this is not going to, this is given to the combustion is 120 megawatt. We need to consider, we need to calculate the followings: thermal efficiency of the cycle, work ratio, power output, and exergy of the exhaust gas leaving the turbine. So, this should be equivalent heat addition given to. So, this is not going, this should be given to. So, we can solve the problem. First, as I had discussed many times, we need to tabulate the data given in the problem statement. So, here it is given that T3. So, if we draw the TS diagram, this is the TS diagram. So, this is P2, P equal to P2, this is P equal to P1. So, this is 3, 1, 2, 3, 4. Okay. So, T3 is given, that is maximum temperature, that is 1050 Kelvin, T1 equal to 300 Kelvin, P1 equal to 1 atmospheric pressure, and it is also given that the air is compressed to 8 atmospheric pressure. So, 1 to 2 is the compression process, we have discussed so many times. Now, P2 equal to 8 atmospheric pressure. So, therefore, Rp that equal to compression ratio equal to P2 by P1 that equal to 8. So, we can write all these from the problem statement. So, what would be the cycle efficiency? So, therefore, eta cycle equal to 1 minus 1 upon Rp power gamma minus 1 upon gamma. So, it is given air So, we can consider gamma equal to 1.4, and if we plug in the value here, that is 1 minus 1 upon 8 power 0.4 divided by 1.4, and it is coming as 44%, 0.44. So, this is the cycle efficiency, right. So, the first part of this number 1, that is solution of this first part of the problem is thermal efficiency, and that is 44%. Now, from this TS plane we can also calculate T2 by T1 and T3 by T4, because these two are the compression and expansion using air air standard equation, ideal gas equation. So, T2 by T1 that equal to P2 by P1 power gamma minus 1 upon gamma, and P2 equal to P3 by P4, that P1 equal to P4. So, gamma minus 1 upon gamma, that equal to T3 by T4, right. So, this is also Rp, this is also Rp. So, from there what we can calculate is, that from there we can calculate T2 equal to T1 into Rp power gamma minus 1 upon gamma. So, that is 543.43 Kelvin. So, we know T1 because T1 is 300 Kelvin, and Rp, that is P2 by P1, that is 8. So, this Rp equal to 8. So, we can calculate T2. Similarly, we also can calculate T4, that is T3 divided by Rp power gamma minus 1 upon gamma, and it is coming as 579.79 Kelvin. So, this is the problem temperature value. You can understand that the rise in temperature of the working fluid at the end of the compression is even less than the temperature of the exhaust gas. So, substantial amount of energy is getting lost, because T4 is even higher than T2. Okay. Then next we can calculate the compression work, WC, that equal to Cp into T2 minus T1, right, and that if we write, that is 1.005, T2 equal to T2 equal to 543.43 minus 300, and that is kilojoule per kg. And expansion work or turbine work, that is Wt equal to Cp into T3 minus T4, and that is 1.005 into T3 equal to 1050, that is given, and T4 equal to 579.79, unit is again kilojoule per kg, right. So, work ratio that we have to calculate here for this problem, that is Wc minus Wt minus Wc divided by Wt. So, this should be Wc only, this is Wt, and if we calculate it, it is coming as 0.48. So, work ratio is very less, 0.48, and finally, we have to calculate power output. So, we know that this is the power output. So, this is eta cycle into Q in, because we know the cycle efficiency, power output but total work output by Q in is equal to cycle efficiency. So, instead of work we are writing power output is equal to eta cycle into Q in. So, what is Q in? So, we have to calculate Q in, otherwise we cannot obtain power output. So, this is one answer, that is work ratio. Cycle efficiency is another one answer. So, next what we can do, we can calculate the heat addition to this unit. So, heat addition cube in equal to m dot Cp into T3 minus T2, and that is equal to given that is 120 megawatt. So, in the last slide, so this eta cycle equal to given, that is 0.44, and this is equal to 120 megawatt. So, this would be 52.8 megawatt. So, Q in is already given, we have no need to calculate Q in, that is already given 120 megawatt, because in the problem statement it is given that the heat addition because of this combustion is equivalent to 120 megawatt. So, this is so this is 120 megawatt, that is this kilowatt. So, from there we can calculate m dot, that is 1 to 120 megawatt divided by Cp into T3 minus T2, that is 1050 minus 543.43 and equal to, and this Cp is equal to 1.005. So, 1.005, and this is coming as 235.70 kg per second, and the final part of this problem is energy flow of the exhaust gas, exergy flow of the exhaust gas, that is delta S, that is m dot Cp T naught into T4 by T naught minus ln T4 by T naught. So, here we have already calculated mass flow rate, we know Cp, this is 1.005, mass flow rate is 235.70 kg per second, that is kilojoule per kg Kelvin, and T4 already we have calculated, and this T naught is T ambient, that is 300 Kelvin. So, already T4 we have calculated, and this T4 is 579.79. So, we can understand that in this expression, this is the exergy flow of the exhaust gas. So, amount of exergy energy that will be released with the exhaust gas, this is the expression. I am very much sure that you know this expression because you have studied it in basic thermodynamics course. So, knowing the mass flow rate that we have calculated from here, we can easily calculate what would be this quantity. So, to summarize, we have solved two different problems, and while solving these two different problems, we have tried to illustrate the concept that we have learned from the theoretical discussion of this particular module of this course. I hope you have learned the steps those are needed to follow while solving a particular problem. As I said that these two problems are the last problems of this particular course, and I wish you all the best. Thank you.